Thanks all for the introduction. And as he said, as a U of M alum, it's good to be back. I've been coming to these summits since I was a grad student back in, I guess, 2010 was the first one I think that I came to. These days, I live in Boulder, Colorado, where I do a lot of rock climbing on these kinds of rocks. And in my free time, I have a day job as a professor at the University of Colorado. And so today I'm going to be talking about my research that I've been working on with students there, as well as some researchers here and the University of Illinois and BBN on our research on deploying anti-censorship in the network. So internet censorship is a global problem that has been getting worse over basically since maybe the last decade or so. And you've probably heard of the big players in this space, right? China and Iran, but even other countries in sort of the Middle East and Southern Asia have different kinds of censorship, and every country seems to do it slightly differently. But there's a lot of players in this space, and this space seems to be growing. The number of countries that do censor their internet every year continues to increase, and the ways in which these countries censor their internet gets more sophisticated every year. So how does a country, say China, censor their internet? And I use China as an example, both because they have a very sophisticated censorship infrastructure, but also because they have a very pretty outline that most people can recognize, unlike some of these other countries that look mostly like rectangles. So how does a country like China actually censor its internet? So a country like China has, the government owns a lot of the routing infrastructure and the telecommunication infrastructure in the country, and especially at the edges of the network, where they peer with outside entities, outside countries, and network providers. And so a user that wants to access a website has to traverse these edge routers at the edge of these networks to get to the websites that they want to visit, say Amazon, Facebook, or Twitter here. And so if they access an unblocked website, then the router just says, well, that's not something that I have in my blacklist. I'm not going to block it. So that's allowed through, and they can receive that traffic. But if they try to go to a website that is blocked, for example, in China, Facebook and Twitter are both examples of websites that are blocked, then these edge routers will notice that this packet is going to one of these blocked destinations and drop it, not let it go through. And there's a bunch of different techniques that censors can use to prevent a user from getting to the website. They can block at the IP layer. They can do DNS injection. So when you try to look up facebook.com, you receive a spoofed packet in response. They can also do deep packet inspection, where if they notice censored keywords over, say, HTTP, they can send TCP resets, for instance. There's a lot of different techniques, but at the end of the day, there's a router here that's sitting between you and the website that you want to get to that can make this determination of whether you can get there or not. So people have come up with countermeasures to get around this previously. You've probably heard of, well, what about proxies? What about VPNs? And these do tend to work, right? That you can, if you're a user in this censored country and you want to get to, say, Facebook or Twitter, you can use a proxy, say, like the Tor browser, which allows you to connect into a network or even just a single host, and use that host as a proxy to make that request on your behalf. And because that's not the thing that's blocked, this will allow you to sort of get around the censorship in this way until the censor discovers that this is being done, that this is a commonly used technique, and then they can just block access to this proxy in the same way that they block access to the websites that they don't want people to visit. And of course, you can then go and say, well, I'll find another proxy and use that, and so I'll use this ultrasurf proxy, for instance, and that will work until the censor finds that one and blocks it. And so this turns very quickly into an arms race between the users in these censored countries that are trying to find new ways to get around the censorship, and the censor who's trying to discover all of the ways that people are using to circumvent their censorship and block it. And so this goes back and forth, and there are entire companies founded on playing this cat and mouse game, if you will, of trying to get resources into this country without the censor knowing what those resources are. So in our research, we asked the question, is there some way that we can get out of this cat and mouse game? Is there some new approach that we can take here where the censor could even know exactly all the details, all the resources, all the ins and outs of our system? There's nothing secret in our system, really, that users have to know, and allow users to use our proxy in a way that censors wouldn't be able to block this. And so thinking about the internet, if you think about sort of how packets get routed around and how a user accesses some of these unblocked websites, say Amazon in this case, their traffic spends a lot of time outside of the country in routers not controlled by their censoring country, right? So in this example, this user is going through those edge routers that do the censorship, but it also passes through a number of ISPs in some nebulous country that isn't the censoring country. And so what if we could put a proxy at one of these routers here? And in this way, if we could proxy traffic by having the user contact that ISP rather than an individual endpoint, it would be very difficult for a censor to block this kind of communication, right? Because to the censor, this just looks like you're talking to this not blocked website. So how do we do this? Well, we need to have some way that the user can tag their connection in some secret way, and then as this tag comes over the network, our proxy needs to have some special kind of key that can detect that tag and extract it from the network and tell that connection, aha, this user doesn't actually want to get to Amazon, they want to go somewhere else. And the proxy can pick up this connection and then proxy or redirect the traffic to its intended destination by sort of either decrypting the connection or talking to the client through this. And meanwhile, if the censor looks at this connection just looks like it's still going to this unblocked site, to Amazon in this case. And so this becomes a very difficult form of proxying for a censor to disrupt, because they have to make a decision, basically, of if they want to allow this kind of communication to go through, or if they want to block all of these reachable sites that don't really have anything to do with censorship, right? Amazon isn't really complicit in this kind of censorship circumvention. They're kind of just being used as a reachable site, or as a decoy in this case, for this kind of proxying. So this idea has had a lot of names over the years. The most recent name that we have been calling this is refraction networking. If you've been paying attention to this, you might have heard the term decoy routing being used, and if you really paid attention, you might have even heard the term end-to-middle proxying. But all of these are basically the same idea with just a different box on it, but refraction networking seems to be sort of the term that we're converging toward, and I think it's a pretty apt name here, because if you think about what's actually happening, you have a user who's making some connection to one of these reachable sites that's not blocked by the censor, and then inside of that, very covertly, they're signaling something to this ISP proxy that then redirects or refracts their traffic to their actual intended destination here. So as I said, over the years, this is a project that actually started here at Michigan in my PhD, and was originally called Telex. Over the years, there have been a number of other projects that have done similar things and built on top of this, including decoy routing, Cirripede, TapDance, which I'll talk about today, as well as, in this case, Rebound. So the first three of these are sort of the first generation refraction networking protocols, I guess you could say. And the last three are additions or sort of second generation ideas that try to solve problems that exist in the first one. So I'll mostly talk about the TapDance one, which solves a deployment problem and makes this a scheme much easier to deploy. But Rebound has a lot of, and also Slitheen are focused on trying to make it much harder to block these kinds of protocols by a censor that really understands and does a lot of traffic analysis. These are capabilities that we don't believe censors have today, but might have in the next 10, 15, 20 years. And then this year, decoy routing was renamed to refraction networking. So that's a brief history of refraction networking. Okay, so in the original first generation refraction networking protocols, the design called for a inline blocking element to be deployed at an internet service provider. What do I mean by that? What I mean is we have some device, some box that sits in the ISP's network, watches traffic go by, and then decides for some subset of that traffic to not let it go through, right? To redirect it to some site and to literally turn off that flow and redirect it somewhere else. So we approached a number of ISPs with this design. We thought, isn't this great? This is going to solve all of the anti-censorship or the censorship problems that we have on the internet. If only you would agree to deploy this on our networks. And we politely, but indeed did sort of get laughed out of the office of these ISPs. They said, we'll never deploy this kind of inline blocking element in our network. It's just not feasible, not in my network. I have SLAs to care about. I have all kinds of agreements and contracts with my customers that, I'm not going to just deploy your research project in my production network here and have it fall over and then the internet's down, right? So we went back to the drawing board and we thought about this for a while and came up with TapDance, which is this idea that allows you to do the same thing, the same kind of refraction networking proxying, but without requiring an inline element. Rather, we only need a copy of the packets as they go by, right? So this is just a tap. This is the tap part of TapDance that just receives a copy of packets as they go past. And we don't actually have to block any traffic at all. We don't have to have any inline elements that, that determine or redirect our flows. So how does this work? Well, there's a couple of tricks that we use, and I won't get into too many nitty-gritty details of how we actually do this, but I think it's from a high level we can at least talk a little bit about how this works. So we have here, a TapDance client. We have the censor that's trying to block traffic. We have the TapDance proxy with some kind of private key that isn't known to anyone else, but the client has the corresponding public key, and that can be public. And then we have the reachable site that the client is going to use to pretend to talk to. And to this reachable site, this user is going to just make a normal TLS connection, right? Nothing special about this. For TapDance, this is just a normal thing that your browser might make when going to an HTTPS link, for instance. But instead of sending a normal GET request to this reachable site, the client is going to craft inside of the encrypted envelope an incomplete HTTP request, right? This is an HTTP request that doesn't have the 2 pairs of line breaks at the end of it that basically tell the reachable site, this is the end of my header or my GET request, please send me a response. And because this is an incomplete request, the reachable site is just going to wait for the rest of it, right? It says, well, you must have just sent the first part of it, and more surely is to come, and so I'll just wait here twiddling my thumbs until you give me some more of this request. Meanwhile, we steganographically place a tag into this incomplete request in the ciphertext of this message in a way that's observable to the TapDance proxy with its private key, but not observable to the censor who doesn't have that private key. And I'll talk about sort of a little bit about the details of how we do that in a second. And so at this point, because the reachable site isn't going to respond to this request, the TapDance proxy is actually free to respond to this request, again, in an encrypted envelope, pretending to be the reachable site. So now, if the censor looks at this closely, they just see a client made a request or something that looked like a request to a unblocked website, and they got a response back from this website. And all is well with the world, right? Nothing really looks that fishy in this setup. And at this point, the client can send additional requests, which is normal, that you would normally have some kind of TLS keep alives or something like that in your connection, that you could send additional requests for additional images or something like that. And in this case, the client sends the request for where it actually wants to go, the blocked website in this case. And the TapDance proxy at the ISP, well, first, this packet, because it's actually going to have TCP numbers or TCP acknowledgement numbers higher than data that the reachable site has sent, will make the reachable site essentially ignore this traffic, right? The reachable site's going to say, well, I didn't send any data that you're acknowledging, so I'm just going to drop that and ignore it. And that's actually kind of an ambiguity in the TCP specification, but if you actually scan the internet and look for hosts and see what they do, virtually all of them do have this behavior that if you send this kind of data, they'll ignore it. And so again, we are free to continue our conversation with the client, responding with the HTML or the web page or whatever resource they requested from this blocked website. So how do we actually have this covert channel, this tag that goes from the client and tells the TapDance proxy that it would like to be picked up and that it would like to talk to this block domain? So we kind of abstract this away to what we call a Chosen-Ciphertext covert channel. But from a high level, you can think about this as Alice is the TapDance client in the censored country, and Bob is the reachable server, right? And remember that the server has nothing to do with this censorship system. It doesn't know about TapDance or have any kind of special code or anything to work with this. So it's just a normal HTTPS server. So Alice is going to establish some encrypted channel over TLS, for instance, to this server Bob, and Alice can send and receive data to Bob. And what we want is we want Eve, who's actually, in this case, the TapDance proxy, or the good guy here, that is going to look at this encrypted channel, right? She can't look at the plain text that's going across this channel, but she can look at the encrypted channel. And we want, given some kind of key relationship between the client and the TapDance proxy, we want it to be the case that Alice can communicate a message to Eve, and that message won't get communicated to other people, even if they're sort of watching. It might get communicated to Bob since he sort of can see this, but because he doesn't have any special code to do this and he's kind of just an oblivious party, that won't matter. However, we do need this message that when we send this to Eve, we need that Bob, when he goes to decrypt that message, doesn't get something that causes him to say, well, I don't understand what that is. I don't know what that is, and close the connection or do something that alerts the censor that this has happened. So we need some way that this message is both valid in some language to Bob, Bob can understand it and ignore it, but yet conveys some information to Eve. And the way that we do this is by, we can do this with block ciphers as well, but I'll explain it most easily with stream ciphers. So in a stream cipher, in encryption, you have one key that you make a bunch of copies to, and you use AES or some block cipher, in this case, to encrypt just a counter. So you start by encrypting 0, then you encrypt 1, you encrypt 2, and you get a key stream out. And from that key stream, you simply just XOR that key stream to the different parts of your plaintext block, and that gives you your ciphertext. So in this case, we have two plaintext blocks, so we encrypt 0, we encrypt 1, and we just XOR the result of that with our plaintext. And decryption is just as easy. You regenerate this key stream and XOR it with your ciphertext, and you get back the plaintext. But stream ciphers have an interesting property, which we call ciphertext malleability, which is that if you flip a bit in the plaintext, you will flip that corresponding bit in the ciphertext. Right? There's sort of a one-to-one mapping between bits that get changed in one to bits that get changed in the other. And so very easily, you can go in the other direction and say, well, if I want to encode a message, then I can simply say, well, I would like to encode the message 01, 02, 03, 04, 05. What plaintext do I have to send in order for me to actually have that be my ciphertext? It's very easy to compute that if you know the key stream, which as the client that has the key with Bob, you do know that. However, if you just did that, when Bob goes to decrypt that message, he's going to get some garbage, right? Because you now have basically sent random data to Bob, and he's an HTTP server, and HTTP servers don't like random data. They want something that looks like HTTP, and so this isn't quite going to work. However, you can play another trick here where you say, well, you don't have to flip every byte, you don't have to change every byte, you can just change maybe the least significant bits of every message that you're sending here. So in this case, the last 4 bits of every byte in this second plaintext block here, we're going to allow to be chosen by our encoding scheme such that we can encode the message 1, 2, 3, 4, 5 into our ciphertext. So this is exactly what we did. We found, basically we made a fake HTTP header here. This is our incomplete request. You can see that it doesn't end with the pair of line breaks, just has a single one at the end. And we send this xignore header that has basically a bunch of gibberish, but that gibberish is constrained, right? It has some, basically you can think of it as like a base 64 encoding, although it's slightly outside of the range of that. But it's a range of characters that HTTP servers will accept and not choke on and close your connection. And so it's exactly when we encrypt this incomplete HTTP request, we've crafted this xignore header in such a way that we encode some data in this ciphertext here that then the TapDance station can look at and extract a tag. And I won't get into the details of how the cryptography of that works, but just know that if you don't have the private key that TapDance has, like the censor doesn't have, then you won't be able to actually tell that this tag is here at all. This will be indistinguishable from random. This will just look like any other ciphertext that any other TLS connection would send. OK, so that's sort of the details of how TapDance works. Thinking back that the motivation was that this is something that's easy to deploy, that we can actually put in ISPs. How did we do? Well, we went back to many, some of the same ISPs and some new ones, and talked to them, and actually found 2 ISPs that were actually willing to deploy this particular scheme. And one is Merit here, which is, many of you know, the upstream to University of Michigan, and actually is the largest, I think, network in the state of Michigan. And the other ISP was the University of Colorado. So we were able to get taps on both of these in different parts of the network and deploy our technology in that network, in that environment. And so the setup for all of this is basically the same across each of these. From a high level, we have some router that's receiving some large amount of data, either 10 or 40 gigabits per second, and it gives us that mirror, which goes to a single NIC on a single 1U server, which has a commercial off-the-shelf NIC, nothing really super special. It's expensive. It's not something you'd put in your laptop, but you can buy for a couple $100 or in some cases a couple $1,000 to fit into the server. And then we have a management interface, and that's actually how we're going to spoof traffic back. We don't have a dedicated injection point. We just use the management interface, and there wasn't any ingress or egress filtering to prevent us to do that in these environments. So in Merit's network, right, this is kind of a view of high-level view of what Merit looks like. It really goes all over the state. We deployed in 3 different locations, 2 in Chicago and 1 in Detroit. And the 2 in Chicago were 40 gigabit taps, and the 1 in Detroit was 10. And then on the University of Colorado network, it was a little bit simpler. There's just one ingress and egress point for the entire campus. It goes through redundant routers, but basically a single point in this case. It splits off into 2 different networks, the science network and the campus network, where most of the traffic goes to the campus network. And conveniently, the University of Colorado already has some intrusion detection clusters running. They're actually running a Bro cluster, although I think Bro is getting renamed, so I don't know what the new name will be yet. But anyway, we essentially just were able to tap into this same switching fabric that they were using, the security team was using, to deploy our station on the 10 gigabit per second mirror of the campus traffic. So we had from the TapDance paper a prototype of the system, but it was really, I think, literally written in 2 weeks, and it was in C, and it was kind of a mess. So we set out to rewrite it so that it would be scalable, and also so that it wouldn't be entirely written in C, because as you know, C has buffer overflows and all kinds of exploitable vulnerabilities, and we were going to open source this, and we didn't want the first thing to happen is a censor finds a 0-day in our code and then just owns this box, and now they have tap traffic of some unsuspecting university or something like that. So so we wrote this code in a combination of Rust and Go, which are both safe languages in the sense that they try very hard to guarantee either type safety or memory safety or data race safety in Rust's case that prevent a lot of these kinds of vulnerabilities. It doesn't rule out vulnerabilities entirely. You can still make mistakes. We can still have bugs in our code and still go wrong there. But it cuts down on the number of things that we have to worry about. And this really helps me sleep at night because now I don't have to worry about a 10,000-line code base of C that was written by 1 or 2 grad students and maybe myself. And who knows if we checked every instance of bounds in every case. So the majority of this is in Rust and in C, or sorry, Rust and in Go. There is a little bit still in C because we have to interface with some specific network cards and network drivers in order to do this at this speed. But the majority of, actually all of the parsing of information and all of the protocol level things are done in Rust on the station. So how does this look from an architectural standpoint? So we have coming in on the left is our 10 or 40 gigabits per second tap. We basically feed that straight to pfring. So this is a driver that lets us lets this library take over a NIC and from the operating system and do some efficient things that it doesn't have to get interrupts per packet or have to worry about the operating system buffering things for it. We can just take it over entirely and run things in pretty much as fast as the hardware will support. pfring also allows us to split out to a number of processes. We split out to either 4 to 16 processes, depending on if we're on the 10 or 40 gigabit tap. And these processes each receive the same flows. So they're doing some kind of load balancing that makes the same flows, the same connections go to the same processes and so forth, which is quite convenient. This gets fed into our TapDance core, which then looks only at TLS packets and does connection tracking for these. So, when it sees a SYN packet, adds that to, found a new packet. And for each new flow, it needs to check if this is a TapDance tagged connection. So we have to do this somewhat expensive cryptographic operation involving elliptic curve Diffie-Hellman that takes on the order of tens of microseconds to actually run, tens to hundreds of microseconds to run per check. So this is something that we have to limit. We don't want to do this all the time. We want to really make sure that this only happens when we need to. But if we detect that something is tagged, then we add it to, we basically create an OpenSSL instance with the correct parameters that can now let us decrypt that connection. And we use this kernel module that we wrote called Forge Socket that lets us tell Linux, give me a TCP socket with arbitrary parameters that I can call send and receive on, and then you can pretend to be any server on the internet that you want, and it'll handle all the acknowledgements and things for you. And then on the other side of that, we basically feed the output of that into a SQUID proxy that then the user can talk to. And so from the client's perspective, they're doing this complicated TapDance thing, and at the end of the day, they're presented essentially a SQUID proxy interface. It looks like they're just talking to SQUID, and so they can plug their browser into that and use the proxy in that way. We also did a bunch of stats collecting and monitoring so that we can get the pretty graphs that you'll see next and sort of see how this system was actually holding up to the scale that we threw at it. So how did we discover the reachable sites for this deployment, right? So okay, we've deployed an ISP, but now actually let's get some real users, right? We can certainly plug it into the ISP and see that our box doesn't fall over. Hooray, success, that's the first step, but we actually have to see if this will support real users. So for that, we need to find these reachable sites that we can have those users connect to and then pretend to talk to them while actually talking to our proxy. And for that, we turn to using Census first to get a list of TLS websites. Census is a search engine actually developed here at the University of Michigan as well that does sort of search engine for internet-connected devices, so backed by doing internet-wide scans and different protocol, talking different protocols to the different IPs. It builds a database of all of these different things on the internet, basically. So we get a list of trusted TLS sites that are in these two ASs, in Colorado and in Merritt. And not all of these will pass by our particular taps, but in this case, most of them did, and so that was sort of our filtering criteria. But this isn't sufficient for saying that all of those can be reachable sites. We have some constraints that we have to abide by in TapDance. In particular, they have to not time out after a certain period of time, and they have to have a certain size TCP window when you open the connection. And so both of these parameters, we had individual tools to actually go and probe each of these individual sites and see what those parameters were, and then throw out all of the sites that didn't have those, that didn't meet the constraints that we needed. Then from that list, we actually used a real TapDance client to talk to these websites and see that you could actually use the TapDance client to talk to the proxy and actually get real service from this, and that this, there wasn't some other underlying thing that we didn't know about that was going to prevent this from working for lots of users. And at the end of the day, we get a list of TapDance compatible reachable sites that we can then give to clients. We basically reserved half of those in our back pocket so that, if something went really weird, we could maybe use that other half or something. We could do some kind of testing. We never had to do that, so we had essentially 450 reachable sites that we could hand out to clients from these two ASs. So the TapDance client was actually entirely written in Go, which is great, so don't have to worry about buffer overflows there either. And we integrated this with Siphon, which is a company that makes a pretty popular anti-censorship app that's deployed in a number of censored countries, and they have millions of users around the world. And we integrated the TapDance module into their Android application and deployed it through sort of a remote update that they had to about 70,000 users in censored countries over the course of about a week or two. So what happened when we did that? Well, this is a little bit rough to see, but hopefully you can kind of make out the outline here. So this is the graph over about a month view of the total traffic that our taps saw. There's 4 different taps here, and this is sort of a stacked graph of all of them. At the upper end of this is about 60 gigabits per second at peak across all of them. And you can kind of see the diurnal pattern here, and also the weekend pattern that seems to be the case for universities, right? So we have the 5 days of the week and then the lulls of the weekend for this graph. And if we map this to the tag checks per second that we actually have to do, the number of new TLS flows that we actually have to see, oh man, you really can't see that at all. We find that at peak, we have to check about 20,000 tags per second. And so if you do this across enough cores, it actually turns out that this was not too bad. This was taking on the order of 5 to 10% of our CPU load, just checking the tags for incoming connections. For active TapDance sessions, this is actually now looking at a week-long view. We had up to about 4,000 concurrent TapDance sessions across all of our users simultaneously at the same moment. This is a much finer granularity graph of one that I'll show later that's over a day. But being able to sustain 4,000 users at the same time is a pretty good result for just having sort of, a handful of boxes. And so the peak load on one of these boxes was approaching, I think, about 50% of that, so upwards of 2,000 concurrent users on a single box. The user traffic, we pushed about, I think, 600 megabits per second of good put, essentially, of user traffic at peak during this trial. And actually, we saturated a 100 megabit per second link during this trial, which you can kind of see here in this pink line. Once we noticed that we had saturated that, we had noticed that that was actually preventing additional users from joining our network. We moved users around by switching which reachable sites went where, and actually moved them off to a different site. And that was sort of a heroic effort on Merit's part of moving traffic around in a particular way to make it so that we could route specific users past our TapDance stations, which is an interesting trick that you can play here. If you look at sort of the reachable site load, you can't see the axes here, but this is basically one question we had was we built a lot of infrastructure around making sure that no individual site was going to get hit by too many users at once and being used for this system. We had several back-off mechanisms and emergency switches and things in place, and had to use none of them because it turned out that we had done the math correctly and that it all kind of just worked out. And so the peak load that any reachable site saw was on the order of 30 to 40 concurrent users that had connections open. And there's really no CPU or any kind of high bandwidth constraints that the reachable sites have. The biggest bottleneck that they have is after they exceed their connection pool, which for Nginx and Apache are on the order of hundreds of connections, then they stop accepting new connections. So this is something that we had to be cognizant of and try to engineer around. But we didn't run into any of these problems. We also had sort of notifications that we sent in these GET requests that would allow site maintainers to know, hey, this is us, here's how this works. If you want us to remove us from the list of reachable sites, contact us here. We didn't have any problems with that, and nobody reached out to us. Looking at the unique users over our peak week, we actually saw on the peak day a little over 55,000 unique users from these censored countries that actually were able to access our proxy. We also tracked session lengths, and there's an interesting sort of network effect here that we're hopefully going to look into more, that it seemed like session lengths were fairly short on average, in the median about 2 minutes or so, although the client was designed so that it would reconnect if it had some kind of failure. We suspect that this is due to sort of some poor network environments in which a lot of these users came from, and we saw a lot of evidence in that in looking in our logs, but we want to learn a little bit more about that going forward. So what did we learn from all of this, right? We deployed this thing to 4 different ISPs. We ingested basically an aggregate about 100 gigabits per second, or the capability to ingest 100 gigabits per second of traffic. I think the biggest takeaway for our team and for this effort is that refraction networking is possible at scale, right? That this is something that we can do, something that we can actually deploy in a network should we have the ability to do so. And I think this is a big step forward, because when we started this project in 2011, this is something that most academics looked at and said, well, that's a neat trick, but you'll never get any ISP to actually do it. And now we have a couple of ISPs doing it, and hopefully more in the future. More concretely, I think there's a lot of lessons that we learned on the technical side and on the operational side especially that we're going to focus on going forward. In particular, thinking about how to do reachable site discovery a little bit smarter, especially when you don't have necessarily a sort of surrounding an entire AS, for instance. If you only see some fraction of that AS's traffic, this becomes a little bit harder of a problem. We also had a trade-off between sort of privacy and the useful data that we collected. We really erred on the side of keeping the data that we collected private for our users and emphasizing user privacy. I think that if we were to do this again, we would probably lean a little bit more toward collecting more useful data so that we can iterate and learn faster. It really took us a long time to sort of sort out some of these problems that would have been faster had we had a little bit more information, say per user experience stats or something like that from our users. So looking forward, there's a lot of organizational stuff that we can do. As I said, longer term deployments. This is something that our team is working on over the next year or so, and heading toward a sustained long-term support for this kind of proxy. On the technical side, we have a bunch of things, coordination between stations and simulating network environments and all of that. And also adopting some of these emerging sort of stealth technologies like Slodine. But I want to sort of take this opportunity that we had to sort of think like a censor, right? I think that as we deployed this, right, we kind of realized that TapDance looks a lot like, the architecture of TapDance looks a lot like what one might imagine the architecture of a censor to look like. Right? In both cases, you're looking at network traffic as it goes past, you're making some determination about what to do with it, and you're sending some data in response, right? So it's interesting that we've kind of converged on very similar architectures here. And so it occurred to me that maybe we could actually learn things about how sensors operate and from this experience. So not only how we can maybe defeat these sensors, but also what their next steps are going to be. And so one thing that sort of came out of this is a little bit surprising and might not be surprising to some people here, but was maybe a little surprising to academics, is this notion of computation versus state. So when you're looking at a bunch of network packets, you can say, well, I'll either look at every packet and do a bunch of computation on it, and I won't store anything, right? Because it just wouldn't be feasible. And most research papers that thought about what sensors did kind of made that assumption, that most sensors are just going to be doing computation is cheap, whatever, throw more cores at it, but they just don't have the capability to store things because things are just happening so fast. On the flip side of that, you could store a lot more information and then only compute when you need to. And if you do the math of this, if you think about sort of like, okay, 100 gigabits per second is about 14 million packets per second, that gives you about 71 nanoseconds per packet per CPU core to make a determination on what to do with that packet. That's not a lot of time, right? 71 nanoseconds, even if you have 32 cores, now you get up to about 2 microseconds of time per packet that you can spend thinking about what to do about it. On the flip side, there is about 50,000 new flows per second that are going across a 100 gigabit link. And if you keep them for about 2 minutes and you store about a kilobyte of data per flow, that's only 6 gigabytes of state across all of these connections. Right? That's a pretty easy trade-off when your server has 64 to 128 gigabytes of RAM and only 32 CPU cores that are operating on this data. So I think one of the takeaways from this was that, and this is something that we did with TapDance, was that we emphasized a little bit more, we leaned more toward the storing state side of things rather than computation heavy. I think this saved us a lot. And I think sensors will do the same if they're given the opportunity. So what about machine learning? This isn't something that we had to think about too much, although we had some ideas of maybe we could use machine learning to do X, Y, and Z, and it's the hot new area, so why not? But this is something that a lot of research has gone into about detecting different kinds of proxies using machine learning. And so how does machine learning work for those that haven't really heard of it? Well, I'm not an expert, but I can tell you from the high level, the basic idea for detecting proxy traffic is this is essentially a classification problem. And how this works is that you have some model here, some machine that you're going to give it two kinds of data. You're going to give it labeled data. First, you're going to give it data that's labeled as, this is proxy traffic. See, look at this. This is proxy traffic. OK, you understand that. Here is some non-proxy traffic. Here's some normal traffic. And you give both of these to this machine, and it outputs some kind of model or classifier or some program, essentially, that when you feed unknown things into it, say, what is this? Then it can tell you, aha, well, that looks like proxy traffic, right? And this is really just, math and modeling that's going on under the hood. There's a bunch of different algorithms that do this, but from a high level, you need this kind of training data to operate on this kind of architecture. And so then if you give it, something else, then it says, this is normal traffic, right? And hopefully it doesn't make too many mistakes, right? However, if you think about the environment in which a sensor lives, they don't really have access to really good training data. In particular, they have tap data, right? They can look at their network traffic and they can see, oh, well, I have 100 gigabit per second of traffic, and I can take it apart and maybe look at it and see what's there. But they don't know the ground truth. They don't know if that TLS connection is actually a TLS connection to Amazon, or if it's just one pretending to talk to Amazon and actually talking to some domain fronting proxy or something like that, right? So they don't have this very good labeled data, and so if they tried to feed this into a machine learning model, they would almost certainly overfit or get it wrong, or basically noise in, noise out, wouldn't get anything useful for that kind of system. Compounding on top of that, there have been research papers, this one from I think 2015, that have done machine learning and actually have had a fair amount of success when they do have access to good training data, which academics often do because they're not these censoring countries. So they can just tap their university traffic or something like that and just label all of that as normal traffic, because almost certainly none of it is obfuscation traffic trying to get around a firewall or something like that, and then generate their own obfuscated traffic to circumvent this. And when they do this, they actually find, using neural networks or even very basic Bayesian classifiers, that they get really good true positive rates. I mean, in some cases, perfect true positive rates, 1.0. Every packet that actually is an obfuscation tool, they're able to label correctly as that was an obfuscation tool. On the flip side, the false positive rate is also very good. The amount of times that they label something that was normal traffic as an obfuscation tool and incorrectly block it is fairly low, right? It's on the order of 0.1% or something like that. But if you think about, and this paper actually makes this argument, that even 0.1% of a false positive rate might not be sufficient for a censoring adversary. And the reason for this is sort of the base rate fallacy here, that most of your traffic that you're looking at is not proxy traffic, right? It's probably maybe 100,000 new flows per second countrywide, but only 10 of those flows per second are actually proxy traffic. And so if you take your true positive rate that's perfect and your false positive rate that's almost perfect, but not quite, and you apply it to this traffic, you'll detect all of the proxy traffic, but you'll also detect 10 times as much benign traffic and mistakenly block it. Right, so you have a really abysmal rate at detecting which flows are actually proxy traffic and which flows aren't. At the end of the day, you really only have basically a 10% accuracy. So I think this is a really hard problem for censors, and this is probably one of the reasons why we don't see censors doing this kind of machine learning or these kinds of heuristic-based approaches that have non-zero false positive rates. This is why instead we see the kinds of things that Roya was talking about, where the censor does sort of active denial of service against different websites or injecting things, right? These are sort of the censor thinking outside of the box, given that they have this interesting constraint. So looking forward, where is this going to go? Well, I don't know, right? I don't have a magic crystal ball here. I can't tell you for certain this is what's going to happen. But thinking about this a lot, I think very obviously the censors are going to continue to censor, and the anti-censors are going to continue to anti-censor, right? So I'm going to keep doing what I do. They're going to keep doing what they do. But I think the arms race balance is shifting. I think we're kind of going through a time now where the censors are starting to run out of things that they can do next, right? We've sort of hypothesized as academics, well, certainly they could do machine learning, they could do these kinds of inferences and detection, but I think maybe they're going to have a little bit more trouble doing that than we previously thought. They might shift their effort to denial of service, like the Great Canon. They might also shift their focus to non-technical discouragement, right? So China has this social credit score thing now, and maybe even just the threat of someone watching and being able to detect that you're using a proxy is enough to discourage you from actually attempting to use one, even if that threat is not correct or is not backed by any technical reason. It might just be the fear of it is enough to keep you from using these tools. On the flip side, the circumvention next moves, I think we're going to see more of these in-network proxies. So not only refraction networking, but we also have tools now, domain fronting, which I mentioned but didn't really talk about, is a popular way that people can reuse CDN networks, or content distribution networks rather, to essentially disguise traffic talking to proxies located in those CDNs. And this is sort of a more limited scope version of kind of doing these in-network proxies, but seems to be fairly effective to this day. On the flip side, we can also do denial of service. The circumvention tools can try to denial of service the firewalls themselves, right? They're doing some kind of deep packet inspection. We can send them traffic and overload their firewalls, and maybe they have to back off their kinds of heuristics. And I think maybe looking forward, there could be ideas of doing automated proxy creation. Some people have looked into this a little bit of ways that you might be able to, from just a packet capture or something like that of benign traffic, be able to construct some kind of obfuscated tool that tells you, oh, this is the kind of proxy that you should design, and this is what it should look like, and it'll be really hard to block. But ultimately, I think this is a pretty exciting space, and I'm happy to have a team at Colorado and also people at Michigan working on this, and also sort of a broader community of people doing things related to censorship, such as Roya doing measurement and other network security things in this space. So I think this is going to be a really exciting time going forward, and I'm happy to have gotten the chance to talk to you today. So thanks a lot. I'd be happy to answer questions.
Well, questions for Eric?
If your client is open source, what would
prevent the censors from treating it as a virus and,
Yeah, so if the censor treats it as a virus, they can do a couple things. They might say, well, we're going to install some program on every computer in our country and make sure that this other software doesn't get installed. And some countries actually tried to do that. In particular, China tried to do this with what's called the Green Dam software that was meant to do this. Ultimately, that effort was unsuccessful for a number of reasons, and no country has successfully been able to mandate this is the operating system that you'll run, or the antivirus that we prescribe that everyone must have by law, or something like that. It doesn't seem to have gotten much traction. So a lot of the censorship circumvention relies on this assumption that there isn't such a sort of antivirus or nanny-net tool or something like that on the individual's computer preventing that.
So you mentioned that you're using hiding techniques to make the tag invisible, but you also mentioned that machine learning or statistical analysis, I think you talked about that as well. So do you think it is detectable? And if it is detectable, when you said you have like a 100% true positive rate, that would still seem to be beneficial to the censors to try to block if they've detected that.
So as a note, those true positive rates were not for this kind of proxy, but for other obfuscation tools that sort of existed before this and are sort of the state of the art now. But nonetheless, we don't see the censors employing those techniques that have been written about and talked about in academic papers in practice. I suspect that if you tried to use machine learning against the tag specifically that we have, the Stegner effect tag, it would be entirely unsuccessful. You wouldn't have anywhere near, you would probably be able to know better than guessing. In fact, we have cryptographic proofs that show that you shouldn't be able to do better than guessing. However, there could be higher order network traffic fingerprints that might exist that you could apply this to, packet sizes, timings, round trips, all that sort of thing. Those distributions may allow you to actually distinguish, and there actually have been a couple papers that have shown that, yeah, it's maybe possible for this kind of technology to do this. Some of the papers that I referenced, like Slaline and Rebound, address that and make that go away entirely. So
since the traffic, just to clarify, since the traffic is already encrypted, you're saying, would it be fair to say that there's no change in entropy as you change the
yeah,
the tag?
That's correct. The tag is encoded, is replacing ciphertext that has a uniform distribution, and the tag itself has a uniform distribution and is indistinguishable from random unless you have the private key.
All right, thank you.
So, yep.
Seeing no one else at the microphones, let's give another round of applause to Eric. Thank you very much for coming back and sharing with us.